At 0300 hours Greenwich Mean Time, in stormy conditions, an explosion occurred on board a 10,000-ton motor ship. The cause? A furnace collapse in a fire tube boiler due to incorrect chemical treatment failing to prevent scale formation. A few days later, a stoppage at sea occurred on a VLCC due to tube failure in a high-pressure boiler as a result of corrosion. Thousands of ships of all sizes operate on the high seas with good standards of boiler operation. There are many different types of boilers operated by marine engineers. Why is it then that occasionally disaster occurs? Something goes wrong with boiler operations, resulting in extensive damage, possible loss of life, and withdrawal of the ship from service for long periods. The causes of breakdown may be many, but they can be avoided if the operating parameters of the boiler in use are rigorously maintained. That and good water management will ensure the safe and cost-effective operation of any steam generating plant. The function of any boiler on board ship is to generate steam from water by applying heat to it. The process of turning water into steam takes place in a metal container where heat is applied to the metal wall. The water, acting as a cooling agent, takes the heat away from the metal, which would otherwise reach a temperature in excess of the metal's melting point. This process takes place in all fired boilers, whatever their design may be. An ideal condition of boiler operation is achieved when the heat transferred from the burning fuel to the water takes place at the optimum efficiency set by the designers of the boiler. However, in reality, there are variable quantities of impurities and contaminants introduced into the system by the water itself, causing a drop in the efficiency of this heat transfer. Dangerous conditions will develop in the boiler if these impurities reduce the rate of heat transfer, either by forming a scale on the surface of the metal or by causing corrosion, thereby weakening the wall of the tube, which can rupture under pressure. We're going to deal with these problems as they relate to the low-pressure boilers of both fire tube and water tube construction with operating pressure below 30 kilograms per square centimeter. Also to waste heat recovery boilers and high-pressure water tube boilers. First, we establish some important facts about water. A common factor in all boilers is water. Its quality and its impurities are critical factors in the operation of any boiler and its associated systems. Water is the most universal solvent. A sample of water will contain a variety of dissolved and suspended matter, in particular hardness salts and dissolved gases. It will contain calcium bicarbonate, calcium sulfate, magnesium chloride, sodium chloride, and other substances in variable quantities, depending on the source of the water. The impurity levels can be as low as just a few parts per million, or as high as 30,000 parts per million, as in seawater, for instance. If untreated shore water were fed into a perfectly sealed system, which circulates without loss, a theoretical condition, the impurities could be dealt with once, and the boiler would operate satisfactorily until it was shut down. In reality, the boiler water and feed system are contaminated by the impurities contained in the replacement of water lost. The amount of make-up water required is a vital indication of the degree of contamination introduced into the boiler. If seawater, through any source, enters the feed system, the contamination will rise very rapidly and must be acted upon immediately. It is a most important principle relating to boiler operation. The make-up water consumption should be monitored continuously and recorded accurately. This is why water may have to be treated to reduce any impurities present to recommended levels before the water can be used in any boiler. The marine engineer has to ensure, 1, that the required quantity and quality of make-up water is available for the boiler. 2, that the boiler is operating at the correct water level. 3, that all impurity levels are below those prescribed by the boiler designers and the chemical manufacturers. 4, that the recommended levels of chemical reserves in the boiler water are maintained at all times. Some boilers have been designed to operate safely using water from a variety of sources. The impurity levels tolerated by such boilers may vary widely. However, the continuous use of water with high levels of impurities inevitably requires a much greater quantity of chemical treatment. The resulting increase in total dissolved solids and extra sludge means more frequent blowdowns and higher costs in terms of used chemicals and fuel consumption. In addition, any neglect of the correct application of chemical treatments and operating procedures will result in the rapid deterioration of the boiler condition with subsequent boiler failure. The real solution is the use of good quality make-up water. An evaporator system on board, if run efficiently, will produce good quality make-up water from seawater by reducing the impurity level to below 4 parts per million. For boilers operating below 30 kilograms per square centimeter pressure, this would represent a good quality make-up water, requiring chemical treatment only for dealing with the remaining hardness in solution and establishing the required level of chemical reserves in the boiler. To reduce the level of the dissolved oxygen in this water, it can be heated to about 85 to 90 degrees centigrade in the hot well. The next stage of low-pressure boiler care is the careful monitoring of boiler water condition. The taking of accurate samples is a most important procedure to ensure that the tests of boiler water condition are authentic. The sample line must be flushed well before a sample is taken to ensure a true representation of the water inside the boiler. The sample should always be drawn through a sample cooler for best results. If one isn't fitted, additional care must be taken by gradually slowing down the flow to a trickle before filling the sample container. It is equally important to ensure that the sample is not contaminated by the container used. Tests should be carried out as soon as the sample is cooled by using approved reagents which are within the dates guaranteed by the suppliers. The practical objectives of these tests are the maintenance of boiler water condition achieved by the correct startup procedure and the maintenance of the recommended levels of chemical reserves in the boiler water. The engineer can meet these objectives by accurately recording the results of these tests, sending the records to the chemical manufacturers for observation, and by following any recommendations made by the manufacturer based on the records. This brings us to the treatment of boiler water. Acidic conditions caused by the presence of carbon dioxide must be treated in the boiler. For low-pressure boilers, some combination of phosphate alkali treatment is used for combating both acidic corrosion and scale formation. A combination treatment is essential because only in recommended combinations do the chemicals function efficiently. The dosage of chemicals will be a function of the impurities in the feed water and the results of regular boiler water tests. The hardness salts in the feed water will also be treated by the chemical in the boiler, turning them into precipitated solids, which can be removed from the boiler by blowdown. One of the most dangerous contaminants is oil. It forms an insulation barrier on the metal surface, severely reducing heat transfers with subsequent damage to the boiler. Immediate action must be taken if any sign of oil contamination is found. Eliminate the source of contamination, and if the oil has reached the boiler, take it off load as soon as possible and clean out the boiler and the contaminated system. Refill the whole system with distilled water and add the chemicals recommended by the manufacturers. It is common practice now to install waste heat recovery boilers or economizers on board motor ships, forming part of the auxiliary boiler system. These boilers tend to be a form of coil structure placed in the path of the main engine exhaust gases. This design has an inherent tendency to encourage sludge deposition. These units may be intermittently used, as they may be shut down while the ship is in port. The combined effect of these factors is that corrosion products are returned into the auxiliary boiler when the waste heat recovery unit is started up again, while the accumulated sludge cannot be removed from the waste heat unit by blowdown. Under certain operating conditions, the heat in the main engine exhaust at a particular engine speed can exceed steam requirements. Any method used to control steaming conditions should not reduce the flow of water through the unit. These types of installation invariably form part of the auxiliary boiler system on board motor ships. Their care must be fully integrated in the treatment for the auxiliary boiler itself. Regular tests for the level of suspended solids will also help to avoid high sediment precipitation in the waste heat recovery unit by reducing the suspended solids through blowdown. For this to be effective when a waste heat recovery unit is shut down, the water should be circulated for at least 6 hours to avoid salts precipitation and sludge deposition there. Next, the treatment of boilers during shutdown. When a boiler system may be shut down for a period of weeks, severe corrosion can occur due to oxygen contamination. It is recommended that after a boiler is taken off load and before it has cooled down sufficiently for vacuum condition to arise, additional approved oxygen scavenger reserve should be built up in the boiler water up to 300 parts per million. This level should be maintained throughout the shutdown. The boiler should be completely filled with water to exclude all chances of air entering it. This method will eliminate oxygen as well as keeping the pH level at 10.5. However, the boiler must not be operated with such a high oxygen scavenger reserve. It must be drained and refilled with distilled water prior to restarting. High-pressure water tube boilers, used for main propulsion, typically operating at around 60 kilograms per square centimeter pressure, are designed to operate within much closer limits. The safe operation of these boilers requires a more exacting chemical treatment system and more sophisticated operating methods. The general rule is that the higher the pressure of steam generated, the greater the need for high-quality make-up water and constant, accurate monitoring of feed water, boiler water, and condensate water conditions. High-pressure water tube boilers require make-up water with less than 2 parts per million impurities. Also, the dissolved gases, oxygen and carbon dioxide, must be eliminated before the water is fed into the boiler. A deaerator mechanically reduces the level of dissolved oxygen in the feed water to about 0.005 parts per million. The remaining oxygen then must be dealt with by adding an approved oxygen scavenger. The continuous dosing of an efficient oxygen scavenger, together with a volatile amine, is recommended just after the deaerator. This will ensure that all feed water is treated prior to the boiler. Distilled water, produced by the evaporator from seawater, will contain a certain level of carbon dioxide due to bicarbonate hardness content in the original seawater. Carbon dioxide and water, on condensing, form carbonic acid, which lowers the pH of the distilled water to about 6. This is slightly acid and will slowly dissolve iron. The ammonia produced by thermal decomposition within the boiler distills over with the steam to raise the pH of the condensate to reduce this problem. Too high a level of an oxygen scavenger can introduce a problem, however, when ammonia, oxygen and copper interact. This can be minimized by careful attention to dosing positions to prevent oxygen affecting the copper-containing alloys in the system. The presence of oxygen, copper oxides and iron oxides in the condensate, whether suspended or in solution, can cause possible deposition and corrosion inside the boiler. This is dangerous and is the main source of trouble for operators of high-pressure water tube boilers. To reduce this problem, the application of an oxygen scavenger at the low-pressure stage of the turbine will eliminate oxygen contamination, while increasing the level of pH in the condensate return. Test samples of the feed water are therefore drawn periodically after the deaerator for testing levels of dissolved iron and copper oxides returned in the condensate water. Special containers must be used for these samples because the levels of these contaminants are very low and the sample must not be contaminated. In high-pressure boilers, the correct treatment of boiler water necessitates a more sophisticated test procedure as the contaminant tolerance levels are much lower. The mineral scale formation in these boilers generally does not represent a major problem due to the high purity of the make-up water used. These boilers are mainly subject to deposition of metal oxides and corrosion, as stated before. As the contaminants originate from the external parts of the closed system, the appropriate treatment must apply to the entire system. Even more so when the high-pressure water tube boiler provides steam for auxiliary purposes through pressure reducers. In fact, steam generators are recommended for providing steam for auxiliary purposes as a way of preventing contamination of the main boiler from external sources. The phosphate alkali treatment described in connection with the low-pressure boiler also applies here, using a different chemical treatment system of coordinated phosphate and pH control. The internal care of high-pressure water tube boilers should always be approached with a comprehensive philosophy, enveloping the entire system. Finally, safety and storage of chemicals. There are some important points which must be kept in mind when working with chemical treatments and reagents. They must be kept in conditions recommended by their manufacturers and must be within their date of guarantee. They must be free from contamination in order to ensure that both the tests and the treatments will be an effective means of control. An accurate record must be kept of the date of stock and the quantities held on board. Chemicals should always be held to be hazardous substances. Great care must be exercised in their handling and storage, and all the safety procedures and safety wear must be used as directed by international regulations. The main points of internal care of boilers. For low-pressure boilers with operating pressures of less than 30 kilograms per square centimeter, good quality evaporated seawater or fresh water with impurity levels of 4 parts per million should be supplied as make-up water. The water should be heated to about 85 to 90 degrees centigrade in the hot well in order to reduce the level of dissolved gases. The boiler water in low-pressure boilers must be treated with a combination phosphate alkali treatment according to the levels recommended by the boiler manufacturer. Any sign of oil contamination of the boiler water must be dealt with immediately, eliminating the source of contamination. Clean the system out thoroughly and refill with distilled water. For high-pressure water tube boilers, those with operating pressures above 30 kilograms per square centimetre, make-up water must not contain impurities of more than 2 parts per million, and it must be de-aerated to eliminate dissolved oxygen and other gases before it is fed into the boiler. This make-up water must then be treated by adding an approved oxygen scavenger and a volatile amine to the feed water to help maintain a desired pH level in the condensate water and throughout the whole system. The chemical reserve levels in the boiler water in high-pressure boilers must be monitored with greater accuracy. The application of a coordinated phosphate pH system is often used for this purpose. Boiler water must be tested regularly, for which accurate samples must be drawn from the boiler through a sample cooler. The samples must not be contaminated either by dirty or reactant containers. Boiler water must be tested for conductivity to determine total dissolved solids and suspended solids levels. Boilers must be blown down regularly to reduce the levels of dissolved solids and sludge, thus avoiding carryover. All chemicals used for treatment must be stored in a cool, dark place, and they must be within their recommended date of use. All testing reagents and equipment must also be kept in good condition and free from contamination. These recommendations have been designed to help ensure a safe and efficient operation of any boiler system and should be followed at all times. We recommend that you consult the literature published by the manufacturers for more detailed information.